Welcome to Load Cell Troubleshooting Tips, 7-step process for troubleshooting a load cell. My name is Henry Zumbrun, president at Morehouse Instrument Company. If you have any questions following this webinar, please feel free to email me at hzumbrun@mhforce.com. I'm hoping you become a customer of ours if you are not already. Morehouse is passionate about making good measurements, so I will be giving you every bit of information I can and telling you everything I can about load cell troubleshooting during this time. I am happy to answer any questions at the end of the webinar. If you have them, just type them in the chat box. The information will help you regardless if you are or are not a Morehouse customer. At the end of today's webinar, I will have an incredible bonus offer if you sign up for our new Morehouse Force Measurement Insider and a discount offer on a load cell tester that makes troubleshooting load cells, well, makes it easy. So today we have about 25 to 30 minutes and we're going to cover load cell basics, 7-step process for troubleshooting a load cell using a load cell tester to diagnose problems. First, let's talk about what's in a load cell. Typically, there's strain gauges in a load cell, and strain gauges are used to measure strain. Most force or torque transducers use strain gauges. Strain is the amount of deformation of a body due to applied force. More specifically, strain is defined as a fractional change in length. A strain gauge is a device whose electrical resistance varies in proportion to the amount of strain in the device. To measure small changes in resistance, strain gauges are almost always used in a bridge configuration with a voltage excitation source. Here's a picture of us actually gauging a load cell. This was our old 1,000,000-pound load cell. It's made of Viscount 44, has 16 strain gauges. You can see the different steps from the machining to applying to soldering, and then the final test before it went to NIST for calibration. We no longer use this cell. We've procured a much better cell, but at the time, this was around 2004, 2005. This was a very good cell. It had a lower limit factor of about 100 pounds at 1,000,000. Now our current cell has a 13-pound lower limit factor at 1,000,000. So made a big upgrade. But looking at that, most load cells or force transducers use a series of 4 resistive arms with an excitation voltage that is applied across the bridge. Some manufacturers will also use dummy gauges to eliminate temperature effects. It is important to look at the manufacturer's temperature specification to determine if the load cell is temperature compensated. Some will even say they are, and they're not, so it's important to test for this. The easiest test we've ever done is taking a cell in from the cold outside and put it in our machine and then acclimated it to temperature over the next day or two and tested it again. That'll show if the cells are compensated or not. It's an easy way to do it. So how load cells work? The importance of learning about strain gauges is really to determine how load cells work, because we're going to troubleshoot them. So a load cell signal is converted to a visual or numeric value by a digital indicator. When there is no load on the cell, the 2 signal lines are at equal voltage. As the load is applied to the cell, the voltage on one signal line increases very slightly, and the voltage on the other signal line decreases very slightly. The difference in voltage between the 2 signals is read by the indicator. This is where you typically will get your millivolt per volt. If you're using Hattie, a DSC, an Agilent, or some of the other ones. So now that we know about strain in this, let's talk about the 7-step process for troubleshooting the load cells. We developed this to save time in the process and to be more consistent in our process. Prior to this 7-step process, any tech would do things any way they thought they wanted to, or any way they thought was the best way to do it, and it didn't work out very well. We wasted numerous hours trying to troubleshoot, and then we started asking questions. Did you do this? I did that. I did this, did that, instead of having a concrete checklist. So this is really going to give you the concrete checklist for troubleshooting a load cell. And step one is the easiest. Check for visual inspection or for noticeable damage. If you look at this picture here, you don't need to go any further. Anyone want to guess what load cell's been overloaded? So yeah, it's this one, the one here on the right, completely smashed down, not possible to fix, very easy to spot. Replace the load cell. Step two, power the system up and make sure all connections are made and verify that batteries have enough voltage and are installed. This is very important. You look at the voltage, numerous times we get a system in and the batteries are dead, set everything up, go to turn it on, batteries are dead. Then you have to, sometimes even, you have to take everything apart to get to the battery. So it's important to do that as a first step. And when you power it on, check voltages of batteries if you can. So if everything appears to be working, but the output does not make sense, check for mechanical issues. Some load cells have an internal stops that may cause the output to plateau. Make sure any adapters threaded into the transducer are not bottoming out. If you look at this picture, right here's what we're talking about. This is the threaded adapter, and it should never be removed as it voids the calibration. Lots of people like to take these in and out. What will happen is if you don't get this in right, you can plateau it. You can actually run the threads completely down until you hit the compression stop, and if you do that, and then you screw the nut back in or torque the jam nut back in, you'll have a situation where eventually the load cell will plateau. So we have noticed several people doing this, and if they bottom the thread out in the load cell, it could cause the output to plateau. If the thread adapter has been removed, the cell will need to be calibrated again. You will not repeat. The thread depth in here is quite different. The output is quite different depending on what the thread depth is. So if you've removed this, it needs to be recalibrated. Step 4, check and make sure the leads, all wires, are properly connected to the load cell meter. If the load cell is new and you wired a cable, verify everything is wired properly. So real easy to switch wires, especially when you don't have the colors right. We've seen numerous cells come in with typically red is positive excitations, black negative. The other day we saw someone have blue and black. So it's good to double check. You can use a multimeter and verify the pinouts. Step 5, check for continuity. This is where we're verifying the pinouts. Check for continuity on the cable, pin each individual connection. If the cable is common to the system, check another load cell and verify the other load cell is working properly. So we check continuity. If we still don't see the issue and we have another load cell in the system, we can plug in the other load cell and verify that the cable's good. If the other load cell works well, now we can eliminate the cable. If the other load cell does not work well, then it points us back to the cable. And if we're pointed back to the cable, the next step or a continuation of step 5 is to pin each individual connection. And while you're pinning it, I recommend bending it. So if you have an intermittent problem, which is the worst type of problem, if you're pinning the cable and you can bend it every foot or every 6 inches, you're going to see it eventually in the meter. It's going to show open line, and when it shows open, you know that that's what the problem is, that it's an intermittent connection. So this happens quite a bit to us. The cell appears to be working. We rotate the load cell. When you rotate it, you reposition the cable, and then all of a sudden the load cell doesn't work. The majority of the time that the problem is an intermittent cable, and this can be very difficult to diagnose. So that's why, get somebody else, keep bending the cable and check for the intermittent signal. Step 6, use a load cell tester or another meter to check the zero resistance of the load cell. If you do not have a load cell tester, you can check bridge resistance with a common multimeter. Common multimeter, you can pin, A and D, or if it's a Morehouse shear web, A and D or excitation, C and B or signal. You should get, 350 ohms plus or minus about 3.5. On this particular one, the picture that I'm showing here is signal output of 32.84%. We want that number to be under 5. So if the signal output is over 5, the load cell has either been overloaded or there is corrosion somewhere in the cable or cell. Typically, we're going to see most of the time that it's been overloaded at a signal equivalent of over 5%, at which point you're almost going to have to replace the load cell. So I was saying earlier about bridge resistance. You can check bridge resistance with pins. You can take the multimeter, you can pin pins A and D, and you can do B and C. You can also check RAB, RAC, CD, everything else for symmetry. You're looking for a symmetric system. If you see 349 and you see 370 for the ohms, chances are it's overloaded. If you don't see anything when you pin A and D, the gauge as this load cell is overloaded, and the gauge has more than likely come off the metal. So if everything is pinned correctly and a reading cannot be obtained, like I said, it's become unbonded from the metal. So, and then step 7, check voltage and current on the power supply. It's easy, use a handheld multimeter. Very rarely is this the cause of our problem, but it does happen. And then at that point, you can get a new power supply, or sometimes you may have to replace the meter. If you look at this, we flow charted this. It's a good reference. Is it damaged? Yes, no, no. No visual damage. Does it power on? Yes. So is it performing mechanically? Yes. Are all the wires connected to the cell and meter? Yes. And then it's inspect the meter, check for continuity. Did you find the problem? Yes, no. If you found the problem, for us, we call the customer and requote a replacement cable. If you don't find the problem, is the zero balance acceptable? And then you look if it's overloaded or not. So there's a nice flow chart. Again, if anybody wants a PDF copy of this, they can grab it and they can take the flow chart. So what happens? So we talked about the cell, the last step 7, we're saying is the cell overloaded. What happens to a load cell when it is overloaded? So typically most cells are manufactured to withstand a rated safe overload. This can be usually found on the manufacturer's spec sheet. The mechanical safe overload is typically 150% of rated output. Our cells are shear web load cells. If you have a 5,000 pound shear web load cell, you will not shift the zero balance until you get to around 7,500 pounds. Once you get to that 7,500, you will start to shift the zero balance. This does not mean that the internal components will not be altered if the load cell is loaded past a certain point. So again, that 7,500, you load it past that point, you're going to start to alter the internal components. A good diagnostic tool in checking the load cell is to monitor the load cell zero balance, as I said, to ensure it is within manufacturer's tolerance. If the zero balance is not within the manufacturer's tolerance or has changed significantly from what it has been previously, there is a chance that the load cell may have been overloaded. So today, you check the zero balance is at 1%. 2 years from now, you check it and it's at 8%. Chances are it's been overloaded. It could be a day, it could be 2 days. It's a good tool. If you're checking this, you have a technician that went out and said, I don't know if I overloaded the load cell or not. If you have the baseline at like 0.1% and now it's at 8%, the tech just overloaded the load cell. So what happens when they overload it? Well, residual stresses and strains are introduced into the structure. The past mechanical history of the flexure, gauge alloy, backing, and adhesive is altered. The load cell symmetry is affected, as well as the compression and or tension output from what it was prior to the overload. Strain gauge characteristics are modified, such as resistance and gauge factor, which will modify the temperature coefficients. So effectively, if that overload is showing at that 8%, there's a good chance that the temperature coefficients are shot and that load cell is no longer as good or has the temperature compensation it once had. So, if the load cell has been overloaded, mechanical damage has been done that is not repairable. Overloading causes permanent deformation within the flexural element and gauges, which destroys the carefully balanced processing. While it is possible to electrically re-zero load cell following overload, it is not recommended because this does nothing to restore the effective performance parameters or the degradation to structural integrity. So more on that. All material has what is called an elastic limit. The elastic limit is the point on the stress-strain diagram where the relationship between stress and strain is no longer linear. If material has a load applied to it that causes the stress in the material to exceed the elastic limit, the material will no longer return to its original size after the load is removed. Luckily, we have a nice graph to show this and make it easy. So around this point, this could be our 150% overload. We're good. We're loading. We go slightly over, and as soon as we start going slightly over and we keep loading, we get to this point in the curve. And eventually, we get to a point where there's a break or rupture. This is normally 200% or more on a shear web cell, but around the 150% point, we start to alter, and then eventually we're gonna ruin the cell, and that's called Young's modulus. So what causes this material deformation? Right here to the left is a picture of one of our blocks, sacrificial block we grind, we use when we're doing testing in our deadweight machine or other machines. Typically we're using softer material than the actual load cell is made of, so we don't mark the customer's load cell. Ideally, we shouldn't use this pad at all, and the customer should send the top block with the load cell, but that does not always happen, so we have to use our material. Material with a lower yield strength than what is being applied will deform until the maximum compressive stress is below the material yield point. So basically, deformation until compressive stress is less than the yield stress. So a steep radius concentrates the force over a smaller area and may cause material to permanently deform. This is why we recommend compression loading pads. That's why we have them. That's why we recommend people have them. Top blocks, hardened top blocks, all types of different blocks. Just use the same material for your calibration that the load cell is calibrated with. You want to replicate those results. Using a load cell tester. A load cell tester can be used to properly troubleshoot load cells. We have a video that can be found here. Again, if you want this or have the PDF, just click that link. I think marketing material should have been sent out with this link. So here's how the load cell tester works. You hold the power button for 3 seconds. Unit will boot up. It will need to be calibrated. You want to take shield to bridge, body to bridge, or shield to body measurements. Typically, you're not going to do that. You're going to be more concerned with, hey, what's my signal? What's my sense? What's my input and output? And what's the that zero balance? But to calibrate it, you can press on and off button with the down arrow. So a load cell tester, what can you use it for? As I said, you're going to be primarily concerned with input and output resistance, resistance difference between sense and excitation leads, signal output, and then these other ones, shield to bridge, and shield to body. These are all things that can help diagnose problems. And important to note that if you want to know linearity, the Morehouse load cell tester will also display linearity. It's a separate mode. You can go to it and start applying capacity and see how linear the device is. But so what we're really concerned with is input or output resistance. If the resistance is not in range, there may be a cable or connector problem. There may be an internal damage to the bridge of the load cell. This is the point where if there is internal damage, if you're lucky, it's just a solder joint. If you're unlucky, the load cell's been overloaded and something's happened. Check the manufacturer's specifications to know what the resistance should be. The tester should allow a value within plus or minus 5 ohms of what the manufacturer states. If the sense is too high, which you can get that warning, sense is too high, the sense lines may not be connected. Or if one of the sense lines readings is high, then there's probably a cable error. Again, go back, troubleshoot the cable. Signal output is too high. Typically, if the signal output is over 5%, the load cell has either been overloaded or there is corrosion somewhere in the cable or cell. The ones that we see are always overloaded. So if you're in a rough production environment, you may deal with corrosion somewhere else in the cell. You can use a tester to test shield to bridge, and shield to body. The load cell insulation resistance specifications for load cell body to bridge is typically greater than 5,000 megohms at 23C. On the tester, shield to body is greater than 5,000 megohms. We typically do not recommend that the shield is attached to the load cell body to prevent ground loops, so the shield to body or bridge will generally meet the same specification. This will most likely be, greater than 5,000 megohms, and the meter will flash red if it's not okay. So that's typically how you use a load cell tester. I'm going to talk about, earlier I said there'd be bonuses for today's webinar. Some things we offer for the Morehouse Insider. If you join the Morehouse Force Measurement Insider, we offer free reviews of calibration certificates from other suppliers. If you're the one that is issuing a calibration certificate and want to send it in and say, hey, how does this look? Am I meeting the criteria? We have webinars on measurement traceability, best force measuring practices, some of the other things. We will look at your certificate and provide feedback. You may not like what you hear, but we'll absolutely provide the feedback and try to make you better. If you have a certificate from a competitor or you just want to know if it's a good, we will try to be objective with it. Typically we see lots of errors in certificates or there's process problems, so we will point those out and you can go back to the supplier if you want with those questions. Another thing we offer is if you have a load cell, you want it tested, we haven't done business before or is something new, we will perform a calibration, send you the data, and you only pay if we meet your needs. This is one of those guarantees. You're not sure that if we're going to be a good fit or our certs are going to be good. We can perform the calibration. We'll go over the data with you. If you're open to going over the data, we'll explain everything, and hopefully then we'll be a good fit to do business together. If we aren't, we can part ways. It's not a problem. Exclusive Excel templates. Currently we're giving out guard banding, a PFA calculator. For those that do not know what that is, that's probably a false accept. There's a new blog on location, and some other things. If you want to learn more about that, you can sign up for our blog. You can go online and read more about measurement risk in these. You would have access to upcoming information on upcoming webinars and training. Access to free merchandise via promotions and special contests. Customize online training for your company in regards to force or torque calibration. So if you have, a few people and you want a one-on-one or a one-on-three or whatever, and you have several questions, we open the mics instead of silencing them like we are now. We open the mics and we can go back and forth and explain things in better detail. Also, articles on force, torque, and measurement-related topics to help you make better measurements, exclusive offers on force calibrating equipment and training, and time-saving tips using lean manufacturing for the calibration lab. So if interested in any of this, I highly recommend you sign up for the Morehouse Force Measurement Insider. So, special offer for today. We talked a lot about the load cell tester. The LCT Ultra is not manufactured by Morehouse. It is an instrument that we like and find very helpful for troubleshooting load cells. Several others retail the LCT. You can go online and shop for it. You can go to our competitor sites and see how much they retail them for. They retail them for around $1,200. Our list is $985. And we are running a $200 off special for members of the Morehouse Force Measurement Insider. So for the next few days, we're offering this special. It's $795, which is $200 off. If you're interested, you want to use it. It saved us a lot of time in our lab. The seven steps that we talked about have saved us a lot of time. This tester, you hook it up, it tells you right away if the zero balance is good or bad, and you'll know a lot more about your load cell and if it's good or bad by using that tester. So I end this. I'd like to thank everybody for staying till the end, and I must ask you a question, and that question is, have you joined the Morehouse Insider mailing list to be notified upcoming webinars and events? And if you have it, and you can email me, do you have suggestions for future blogs or webinar topics? Would you like to write an article for our blog or want a PDF copy of this presentation? If you want any of this, please email me, or if you have suggestions, please email me. At the end of this, I'll answer the questions, but if you have it and you didn't get them and you didn't ask it right now, please email me. And watch for our next webinar. Our next webinar is going to be 4 steps to choosing the right load cell calibration system, and that's coming July 25, and that deals with the types of load cells, what they're good for, the weights, different weights, that whole trade-off. Do I want a cell that's really good, but I'm going to sacrifice, it's going to be much heavier than I want to carry, or do I want something that's very portable for my application? What's the difference between single column and multi-column cells as far as hysteresis, nonlinearity, response? It's going to answer that as we're going to talk about meters, because it is a full system. What's the difference between direct read, millivolt per volt? Going to talk about cal providers, and going to talk a little bit about adapters, those top pads, the things that I briefly mentioned today. So in any case, thank you everybody. I hope to see you at our next webinar, or please feel free to go online and download the on-demand webinars. Thanks again. Bye.